All right. Hi, everybody. Happy Wednesday evening. Welcome back to our AP Physics 1 CRAM session. So the focus for tonight is all about the free response questions, the QQT and the paragraph length response one, the two kinds of questions you guys are going to be focused on for next week's exam. So yeah, exam update, stuff like that. You guys have seen this stuff already. I'm not going to bore you with a ton of it. I do want to point out, though I know some of you guys have watched them already, College Board is doing a YouTube video series of questions and sample test stuff like that. I watched a couple today. They're pretty good, so I would recommend going and taking a look at those if you've got some time. They're about an hour a session, so about the same length as we'll be here for that. Okay, so before we get into the questions, just some tips on writing. Because I realize I haven't done a slide on this, and that would be bad if I don't prepare you guys to write properly here. So basically, the best way to write, and this is for paragraph length response specifically, or it could be qual-quant if they want a long justify sort of thing in there. The mnemonic is not mine. I stole that from somebody else, but it's a CBDA format. You're going to cite the evidence from the problem. What in the problem did they give you that is there? Yeah, Ria, that's exactly where I stole it from. You're going to bring in the basic physics principles, draw them together, and then answer the question at the very end. So it's slightly different from like claim evidence reasoning. This is evidence reasoning claim. But the idea is that you should be at the final sentence, be able to say, therefore, this is my answer, sort of stuff. Other generic stuff, one of the big things is stick with one approach. If you are using energy as your reasoning and your rationale for why something happens, stick with it. Don't jump from energy to forces to rotation to motion, sort of stuff like that. Keep it super streamlined. Don't pull, okay? So if we're talking about projectile motion, stuff falling through the air, we're going to talk about velocities, accelerations, distances. I'm not going to get into energy and stuff like that with those things. So keep it focused. Don't mix and match. Don't say any incorrect physics things. If you are not sure about the physics, leave it out and just answer with your logic. Okay, if you're uncertain. Now, for number 3 there, that correct physics part, this should be pretty straightforward because you guys have open notes. You have access to all the textbook stuff. All the correct physics principles are there. You just got to be able to write them down correctly. Number 4, I kind of said this already, but don't wander off the topic. Stay focused. I don't care about neglect, that we always neglect air resistance or stuff like that. I want to know the acceleration's the same, et cetera, et cetera, et cetera. So, and the last part there is College Board recommends that you type your answers, but they can be handwritten too, if you feel the urge to write out stuff like that. What that means to me is when I got this email, it might mean that we're not doing any super long derivations. So yeah, it should be, even the QQT ones are probably going to be a ton of explain whys and less of the do that sort of stuff. All right, so that being said, I've got a bunch of free response questions, and we're going to kind of just go through this CBDA process. I don't even care if we solve the questions completely, but if we can get the framework set up, just so you guys can speed through them and get that set up well for next week, that's a win in my book. All right, so I'm going to switch over here for a second. Now, let's do bit paper. There we go. Okay, so let's take a look. We'll hold off for that one for a bit here. No, we did that one already. Where is my new one? I was told to do a spring one. Here's a spring one. Okay, so this one, 2 blocks on a spring. We've kind of done questions like this already, but just to go through, this would be a qual-quant sort of problem. And realistically, I'm not expecting part A to show up on the exam, but part B definitely will here. So we have 2 blocks and a dog running crazily upstairs. 2 blocks going on there. They're on a horizontal frictionless surface attached with a spring constant K. The block oscillates with a certain period and about the spring's equilibrium position, x naught. A second block Q of mass 2m gets dropped on it, and sticks to the block. All right, we're supposed to figure out the ratio of the periods. Okay, so this would normally be a math problem. I'm going to try to do it as a paragraph response, saying how would you find the ratio of those things? So first part, citing evidence. Evidence stuff that we know here. We had the mass before was M, after was 3M. What else do I know here? There's no friction. And the same spring, I guess. I don't know if that's going to be important or not later on, but that's kind of where I'm going here. So the same spring, same K value, et cetera there. Okay. B, basic physics principles. Well, they're talking about periods. So the period of a spring is equal to 2 pi times the square root of M over K. And that's probably the only basic physics principle I need right now. The period depends on that. Drawing them together. This is where I'm going to talk about the period of the oscillation. Depends on mass and the spring constant. Spring constant is the same in each case. Period. PQ will be square root of 3 times bigger than TP. So the answer is and now part B and A. So A, I'm just claiming. Actually, I should get to this part. This would be, yeah, you're right. Okay, here we go. Yeah, so if I wanted to polish this up now, my C part would start off with, in the question, in the scenario, spring remains the same. I'll just do that. The spring constant the same, and the increases from M to 3M, and block Q is N. Okay, oh, I should leave that in there. What do I want to do? The period of oscillation. About the period of oscillation is that, and then go from there. So there's my kind of parts in there. Take out the CBDA part, and that's kind of my paragraph sort of reasoning with that. Okay, so cite some evidence. I have the masses and stuff like that. Relative physics, so related equation. This is also where you'd pull in things like conservation of energy or other stuff like that if you needed it. D, draw it all together. Why or how does the evidence match up with your physics? And then A, kind of sum it up, stuff like that. Okay. Questions on that part? And I realize that, yes, this was not a paragraph length response question, but since everything about this exam this year is paragraph length response, let's go with that. Okay, on to the next part then. Now we're doing something different. And now how does the amplitude change? Okay, so the same sort of thing, and this one specifically calls for a paragraph length response. So that's nice. We might as well just start off with that then and go with, again, our C, B, E, A sort of format. So in this case, we're looking at the amplitude. So again, I guess we could say something like, I guess the same sort of stuff, right? No friction. Mass increases from M to 3M. Same spring. Okay. What physics principle are we bringing in here? Because this one's not as cut and dry as saying, oh, it's going to be period of a pendulum or period of a spring, not pendulum, just throwing right in there. What physics principle should we use here? All right. So in this case, there are two big ideas that I could see bringing in, and we kind of get to choose which one we want to use because we kind of have freedom for that. But the two I'm thinking about here, we can definitely do conservation of energy since we don't have friction, and the amplitude part could play into our stretching and stuff like that in there. So conservation of energy, and momentum. Because we're talking about a collision and crashing and stuff like that. So that's a possibility too, is we bring both those parts in there with the appropriate equations and stuff like that if we need to. Okay. So let's go through our details now, or our drawing it together. Yeah, D for drawing, not for details, although they're probably pretty close together here now. So let's part's gonna move a little bit here. Okay, yeah, that's a good one to put in here too. The amplitude and energy one. I guess if we're talking about conservation of energy, we could even pull in, yeah, the amplitude will be X in this case. PES, potential energy in a spring, is 1/2 kx squared. Kinetic energy is 1/2 mv squared. And since we're doing it, conservation of momentum, P before equals P after. Those are the kind of parts here. I was going to put those equations in my details, but it doesn't hurt to put them in there earlier, that these are the relevant things in here. VA equals 1/3. Yeah. And you could show the math and work this part out. This is something I would do on like some scratch paper or something like that, because the derivation is not the important part here. The important part is that we are slowing down. Okay, so we're talking about conservation of energy in there. or sorry, conservation of momentum. Oops. You thought you couldn't use conservation of energy if energy is conserved. Well, energy is conserved means that conservation of energy definitely applies. Isn't conserved, true, but I'm not talking about. Okay, so let's put it this way. I am talking about conservation of energy, kinetic in the moving boxes to potential when it's fully stretched out. I am not saying that we're not losing energy when the boxes smack together, because that is true. But I'm looking at it to say the total kinetic energy of the blocks will turn into potential energy when it's stretched out to the biggest amplitude. Okay? And that's kind of why I am kind of mixing a little bit here. It does talk about less kinetic energy after the collision. Yes, it's inelastic. Yes. Yes. And actually, if I put that in there, that'd be great. Because this collision is inelastic. All right, so after the collision, which means that the amplitude of EQ will be less than of. So I'm saying that since energy is lost overall, but conserved as the blocks make the rate of the highest point. Yeah, so PES and KE are equal. Yes. So if I wanted to compare the entire thing before they collided and after they collided, I have lost kinetic energy in that process. In there. And I suppose I could word this a little bit differently just to draw that out clearer here. Let's see here. Outside forces, total energy, total energy conserved. Okay, so maybe if now I'm thinking about it, let's go back through and reword this little part a little bit here. Is conserved as the spring at the equilibrium point. I can just say A, right? I can just say A. They're calling it A for amplitude. Yeah. at AP. There we go. Then, how do I do this? When block Q is added, yeah, I really need to move this so we can read the whole thing here. I apologize for that. So yeah, when block Q is added, we can use conservation of momentum. See that we have less velocity. Lower velocity will result in lower kinetic energy after the collision because it's an elastic. Yeah. Oh, does that clarify it a little better? So going back through, so we established we can use conservation of energy. We talk about the before collision on there. Then we go through and say, because we've collided now, our kinetic energy is less. It's still going to get converted all to potential energy, but it's got to be less for a swing there and stuff like that. Okay, and then yeah, that's kind of where we're going here. And then do the same sort of thing for the C and B. Put it in there, you know, in this scenario, there is no friction, which means you're not worried about the speed changing because of that. When block Q is dropped, the mass goes from M to 3M, that sort of thing like that on there. Useful equations include, or useful concepts include conservation of energy and conservation of momentum, and then zip through the rest right there. All right, so there is my spring question. With that part, actually, I want to move this. I'll fix it later. Okay. So that's the motion conservation, energy sort of stuff, and your typical paragraph length response sort of thing. It's a good sized paragraph. Now, there's probably stuff I don't need to put in there, or I said over and over again, which is okay. I'm just restating my point. But the goal here is that we didn't vary off. We didn't talk about accelerations and forces and stuff like that, because the plan for this was energy and momentum. All the physics there are correct, and every physics equation we put in added to our argument and didn't take away from something. We're not putting in PES equals 1/2 kx squared just for the fun of it. We are talking about it because we're changing X and therefore we're changing potential energy. Or the kinetic energy one, we changed V, so we should change kinetic energy. That sort of stuff like that in there. I also didn't do the entire conservation of momentum derivation part. I just simply said we end up with the velocity afterwards equals 1/3 the initial velocity. That's fine. We don't need to see the entire derivation unless they ask for it. But I'm going to guess that, especially for next week's exam, they're not going to ask for an entire derivation. What they're going to do is something probably similar to what was done on the AP streams, which is something like this one. Okay, now I know this one's been done a little bit. I just wanted to make sure that we covered it because, well, it's one of those wonderful questions, and it's the most recent question that I've seen from College Board about the way they're going to deal with derivations and stuff like that this year. Because this question was on the course description or course guide book sort of thing that all the teachers got. But what they did was they changed part 3. Part C and D in the booklet they passed out at the beginning of the year were about derive this equation, derive this expression. And here it looks like they're switching into, okay, so we have this equation. What does it mean? Which is, again, more evidence that I think next week we're going to see a lot more questions about, does this equation work? How does this equation work? Why does it match up well? And less about, okay, start with Newton's law and show me that it gets to this particular equation, if that makes sense. So that's kind of where we're going with this. So I want to do this question because I like it. And I think it's a good practice question. I'm going to do it a slightly different way than they did on the stream, but that's fine because we're two different people. We should get the same reason, or hopefully the same physical answers. based on that. All right, so we have a sphere, mass m, suspended by a string length L, and we are going to make it go in a circle of radius r, as shown above. The center of the circle is labeled C, the string makes an angle theta, and they're discussing the motion of the sphere and make some following statements. Okay, so we have the very nice 2 students arguing about something, or 3 students arguing. I wonder how many students we are. Just 2 students. So 2, 3 students, something like that is typically what we'll see here. About who's right and who's wrong and stuff like that. Whoa, that's a red mark. Okay, so 2 students discussing the motion of the sphere. None of the forces exerted on the sphere are in the direction of point C, so it can't move in a circle. And student 2, the tension force is at an angle. Therefore, the vertical component has to be less than the weight of the sphere. This means the net force of the sphere has a downward part. The sphere should swing down as well as moving in a circle. Okay, both of them are wrong, partially. And they're both wrong because the question tells us that they're both wrong about some part. Student 1's wrong for one simple point. Okay. Yes, we have 2 forces acting on the sphere. We have gravity going down. We have tension going over. Yes, but there is a part pointing towards the center. Yep. And that's really all you need to say for this one. There's a force pointing towards the center. Common thing. Just because there's not an arrow that we draw pointing towards the center doesn't mean that there isn't one. And very often, actually, let me think, 100% of the time, the centripetal force will be caused by another force. In this case, it's caused by the tension. Sometimes it's caused by friction. Sometimes it's caused by gravity. But very rarely is there a very blatant thing pointing towards the center of the circle that we say, oh, this gets FC on it because it's centripetal force. Centripetal force will always be caused by another more common force: tension, gravity, friction, normal force, that sort of stuff like that. Okay, what's wrong with student 2? Yeah. Okay, so it's equal to mg because now we have to do the y part. So we said that that's what's true. Now we just have to say because the sphere, right, sphere. I always want to call it a ball. So something like that going through there. Vertical component's equal to mg because the sphere moves in a horizontal circle. Pretty straightforward. All right. So a lot of these times you'll see it either be what's right about the student, what's wrong, and then explain using some equations. I think we're going to see a slight shift on it. It'll be what's wrong, what's right, or what's right, and then how does this equation support it? So in this case, this is all about how the equations support or refute the student's claims. So we have 2 equations here. F net equals FTR over L, and mg equals FT squared of L squared minus R squared over L. These are the things that relate the tension forces to the net force and other quantities. Explain how one of them can be used to challenge student 1's claim, and how the other one can be used to challenge student 2's claim. All right, well, looking at this pretty quickly here, I can see that one of these has an mg in it. And only one student made a claim about gravity, about the weight of the object. So this one has to be done for student 2. Well, that's terrible. Come on, write properly. And that means that this equation must deal with student 1's. So somehow we have to use this first equation to challenge student 1's claim. All right, so let's see what student 1, what this equation is actually saying here. F net must be the centripetal force. This one's got to be the one pointing towards the center to cause it to rotate. Ft is tension, and then R over L. R over L, that's the radius over the length. Okay, so radius would be this way, and length is that way. Is that, it's got to be some sort of trig thing going on here. Yeah, I think it's tangent. Is that what, so let's do some things here. I'm going to just, for the sake of this, call this H, because why not? So sine theta must be R over L. Hey, no, it's just sine. That's all it is just sine. It's not tan. It's just sine. Opposite over hypotenuse. That's R over L. Cos theta must be H over L. And then tan theta will be H over R. No, sorry, R over H, opposite over adjacent. Okay. R over H. All right, so yeah, it's just sine. And this is weird because when I looked at that for the first time, I was trying to think, what does R and L actually mean? Why are we doing this? What is all this stuff coming up for? But yeah, all it really does is that just means that we are talking about this being sine theta. So really what equation 1 is saying is the net force will be equal to T sine theta, using the terminology that I used in the previous one, the tension times the sine of theta. Well, the tension times the sine of theta is the horizontal component. That is the part that's pointing towards the center of the circle. So equation 1, F net equals Ft R over L is showing that there is a net force, and it's equal to the horizontal of tension. Okay. And I think that's good enough. I think that's what it's looking at for that sort of thing. So we can say that, hey, there is a net force and it's equal to the horizontal component. And I guess we could even say a net force pointing towards the center, maybe. Like that probably is more complete. I'm not sure how they would score it part like that. So yeah, so saying R over L is equal to sine theta. Yeah, that's exactly it. I don't know if you need to go that far and say that, hey, this is really saying the net force is T sine theta. But we're saying the same thing. So I'm saying horizontal component, which is T sine theta, and that's what R over L is. So I think either way you want to do it, and saying that net force is tension times sine theta, that could work too. Both of these show that we've deconstructed what that R over L actually means and put it in some meaningful terms for us. So I think that's good. Either way. All right, let's look at equation 2 now. Equation 2 has the same sort of thing where we are saying that we have mg. So that must be the weight is equal to tension, or sorry, let's make that a T, times this wonderful thing. L squared minus R squared over L. Okay. Well, if we know what student 2's wrong about here, yeah, it really should be this cos theta part. And yeah, so it's going to be H. This is Pythagorean theorem. So it should be L squared equals H squared plus R squared. So H is the square root of L squared minus R squared. So yeah, that is the height. So this is definitely one where you're saying, hey, this whole thing is T cos theta in there. So we're back to that same sort of idea here. This is equation 2. Mg equals Ft square root how do I do this? L squared minus R squared over L. So that over L, done. Is showing that the weighted clock is equal to the vertical component. Yeah. Okay. So yeah, there's that part there. Random question. What forces would I put on a free body diagram? So I would put probably the big ones: gravity, normal, tension, friction, and any applied forces. Trying to think if there's any other ones on there. Gravity, always. Normal, if you got a surface. No, centripetal is always caused by another force. So I can't say put a centripetal force on an object. I can say this tension is causing a centripetal force, or gravity is causing a centripetal force, but centripetal force FC will never show up on a free body diagram because it's always caused by tension or friction or normal or gravity or an applied force of some kind. Yeah, so I would never put centripetal FC on a free body diagram. Never, never, never. Okay, moving on then. Students observe that the radius R increases as the speed V increases. So I move the sphere faster, I get a bigger circle. Okay, that kind of makes sense to me. Together they derive this equation. R equals V square root of L over G. To calculate the radius of the circle followed by the sphere if its speed is V. Okay, regardless of whether it's correct or not. So we don't care if it's truthful or not. Yay, don't care about truth. Does this plausibly model what the students are saying? Okay, does this equation show that when V increases, R increases? Yeah, I think so. It kind of does. Yeah, they're both in the numerator. Yes, this equation shows that when V is increased, R increases. Well, I want to say they're both. Yeah, they're both. How about this? There is a direct. Yeah, I was getting caught up. I don't want to say they're both in the numerator because R doesn't have a fraction side on it, and that was just. It's not wrong to say they're both in the numerator. To me, that was just a little. Like V is definitely in the numerator. I don't know if I'd say R is in the numerator. So definitely direct or proportional or something like that. Yeah. On there. Centripetal force is net force in circular motion. Yeah, that if you have uniform circular motion, the centripetal force is the net force. And again, net force is the total forces. It's not a given thing. I can't say, well, I can't say this is a net force. I can say that this force causes a net force, or this force is the unbalanced one, or something like that in there. So yeah, just like centripetal force, I would never put on a free body diagram. It is the net force in circular motion, as long as it's uniform circular motion and you're not changing to an ellipse or anything like that. All right, last part to this one then, I think. This equation, this R equals V squared of L over G, doesn't work very well if V is very fast. So if I make V get very, very, very big, this breaks. Why? And this one took me a while. There's a really good physical reason why. And now that I see it, it's, oh, a duh moment. Like, why didn't I think of that earlier? But It's one of those that if you don't see it right away, that's okay, because this was a little tricky. And let's see if I can. So G can't change. True. So the only other thing that can balance it out is R, and R can't be super big, right? The radius can't change. Well, the radius can change, but as Jeff is saying, the radius has a limit, right? I can't make this circle be any bigger than the length the string is. So eventually I needed to get some point where this radius can't get any bigger. And there's no limit built into this function. This basically says as V gets bigger, R gets bigger. There's no stop at this point. This just basically says go through. Radius changes with the angle. Well, sure, but so does the velocity in there. The big thing here is what you already said there, Jeff, is saying that if V is very large, it's possible that R could become I'm going to put a little calculus in here. If you guys are calc students, you'll get this. Otherwise, it won't make sense. But the math here, so there's the math away there. So yeah, so if you've done calc, it's a limit problem, really. If you haven't done calc, it's just there is some, we can't make it bigger than now. And no matter how fast I spin something around my head, it should go the length of the string and no more. So that's the sort of part there. And if you know calc, absolutely, that limit argument is 100% physically accurate and a good explanation of why. Yes, if you don't know the limit one, that's fine too. But yes, absolutely. If you use calc and you know calc, go for it. There's nothing wrong with that. You just don't have to use it in there. All right. I think this question goes on. Oh, yes, it does. Here we go. Continuing on. Now, this question has like, I think, K parts to it, which is kind of ridiculous for a 25-minute question. B, C, D, E, F, H, I, J, K. You got 10 parts on it. That's like 2.5 minutes per question. So I'd be surprised if you have K parts on a question. But this one, because it's practice, I think they felt like they could get away with putting as much stuff in there as they could. All right, so we got this graph now. We're now turning it into a pendulum. So yay for our second kind of simple harmonic motion. We did springs, we did circles, now we're on to pendulums. The maximum angle theta max makes can be assumed to be very small. Good. Again, this assumption right here, this assumed to be very small part, means that we can use our period of a pendulum equation. If they didn't say that, we would bring that into question as to whether we can use that or not. Oh, so the College Board prep stuff actually had up to I. Okay. So maybe it's going to be, maybe they're thinking qual quant and just kind of jamming a bunch of short things in there, not expecting huge paragraphs for a lot of these. Maybe, I don't know. I guess we'll find out next week. Or you'll find out next week. I won't find out till, wow, June. So it's a possibility. So I guess we'll just keep practicing this one then and go from there. So we're given graph, square the period, function of L. How would the graph change under each of these following circumstances? All right. So looking at this, let's go through the options here. So this is relatively linear. And looking at our axis, period squared and length. That means I can take this equation right here and square the period of a pendulum equation, square it to get my realistic one. So t squared 4 pi squared L over G. All right, now we do our linearizing practice here. Period squared is on the y-axis, L is on the x-axis, and everything in the middle must be my slope because y equals mx, and there's no plus here, so there's plus 0 sort of thing like that on there. So I'm not going to see any sort of part there. So we linearized it pretty nicely in there. And again, I squared everything because the y-axis had period squared and the x-axis had L, not square root of L. All right, so let's go through the what ifs. What things would change? Okay, let's start with the first one here. G. What's going to change if I increase the mass of the sphere? Well, nothing. So that one looks good. Nothing happens there. Yeah, and I would even argue the same sort of thing for H too. Nothing. And we already assumed the angle to be small, so theta isn't in the slope equation. And then yeah, so now we're going to the moon. The moon is going to have a smaller value of G. And since G is in the denominator, we're going to have a bigger slope. Yeah, something like that. So that's kind of how I would write it. It says justify. So I suppose at some point with all this stuff, we would have to actually write out this sort of thing just to justify your answer. And then, so have the derivation maybe in part G saying something like the slope of that line is equal to 4 pi squared over G. Mass isn't in there. Nothing happens to the slope. H, the slope of the line is 4 pi squared over G. Theta isn't in there, so nothing happens to the slope. And then I do the same sort of thing like that. So it may be restating it over and over and over again. Although it's probably okay too. I got to think about how, and this is a question I don't have an answer to. If they have these all in one like text box sort of thing, where you submit everything to this problem as one blurb, you should be okay saying using the derivation in part G, or theta isn't in the slope equation as shown in part G. That sort of thing. So you don't have to write it out a whole bunch of times. You can refer back to previous steps and stuff like that there. All right, continuing on. Another explanation problem. The graph above shows the angle theta from vertical as a function of time for the pendulum. Explain how this graph shows evidence of a net force acting on the sphere and how it shows that this net force is a restoring force. Okay, 2 parts to it. We have to show that this is a net force. So let's do that easy part first here. There's the first part. So simple position versus time. Yes, theta is not a distance per se, but it's still the same sort of thing. It's a position versus time. So we're looking at a changing velocity of some sort, whether it's angular or otherwise. We can always convert angular back to linear. So I'm kind of leaving that and just saying it's changing. So therefore we have a velocity that's changing, which means we have an acceleration. let's see, because the graph is concave down. Okay, so there we go. There's that one right there for that chunk as well. So talking about how we've got, I use concavity. You could talk about how the velocity goes from being 0 to negative to that sort of thing like that too, if you didn't get the concavity argument when you learned it the first time. All right, paragraph length response that the College Board provided. Are you talking about this one? Or is there a different one? No. Okay, let's, oh, there was a no and a yes. Oh, that one. Okay, sure. We can do, how much time we got here? We got time, we got 10 minutes. I can try both. I can't guarantee I can get through both of them, but I can definitely try. Let me quickly grab that one from the College Board one for a second here. All right, so this one I'm showing right now is the one I stole from the live stream. I think they're going over answers to this one tomorrow, so I can't guarantee my answer's 100% accurate, but I'm going to be close to it, hopefully. Otherwise, I need to go back and study more. All right, so in this case, we're looking for a diver jumping off a board. They flip, and then, so yeah, it's jump, tuck, and then come out and enter straight. We're supposed to talk about the athlete's angular speed increasing between 1 and 2, and then decreasing between 2 and 3. Okay, so paragraph length response. Let's go through our stuff again. Claims, basic physics, sorry, cites, basic physics, draw it all together and answer. Okay, so here's my rough idea here. That was something. The clerk's acting on him. Right, so I don't really have any claim or any cite things here, except for they're going through there. This means that angular momentum here. So start defining some terms in there and stuff like that. Do I need to mention torque? Yeah, if I don't mention torque, it kind of weakens my claim about angular momentum. Angular momentum gets to be conserved when there are no external torques. So whether they're going to require that part in there or just allow you to say, hey, this is conservation of angular momentum, that's the part I'm not sure about. You have to watch the stream tomorrow, or I will just steal the answers and let you guys know about it. But you probably should mention something about it just so you can be sure that you're making that claim angular momentum is conserved. Case 1. Diver has a large uses the moment of inertia and free the diver inertia. Okay, did I get everything there? Yeah, moment inertia is the easier one here. Jeff, you said something like the more revolutions, the higher theta becomes. This is the number of revolutions. That's true. But how do you explain the more revolutions? I mean, your statement's correct. Theta is 2 pi times revolutions. Then you'd have to say something. Yeah, you're using the definition of revolutions to see if it will talk about omega, but how are you relating that back to the fact that they can change those numbers of revolutions? Like, why are the number of revolutions changing, and therefore their omega changing as a result of that? So what you're saying is true. I just don't know if it's fundamental enough or physicsy enough to explain why that's happening. You're doing a good job on the what's happening. Now we got to do the why here. Yeah, diver's closer to its center of mass. Its moment of inertia is smaller. The inertia decreases. The inertia increases because there's an inverse relationship. Yes, that's really good. You got the buzzwords in there. You got the terms. You got the equation. You defined what moment of inertia is, relatively speaking. So yes, that's all good in there. That great answer right there for that. So, and I feel like I don't need to do this because I kind of answered parts of that already in there. It depends how much math I want to put in here, but that's kind of the gist of it there. So yeah, that works really nicely there. Okay, let's talk case B because we don't have a ton left here, and then I do want to. I'll go a bit late, and we'll hit that last one too. So case B is the rotational kinetic energy greater than, less than, or equal to the rotational kinetic energy of the athlete in Figure 1. Explain your answer. All right, so Okay, so this is where the wording part's going to come in here. I pondered over this question for a while, so I think I've got the right concept, but it took me a while to try to piece this together. So is there even rotational kinetic energy? Yeah, because they are still moving. They're jumping a little bit. So they are rotating around some center point. I guess if you want to pick their point they're rotating about, it might be like they're still rotating around that point. It's just going to be very hard for them to bring their parts around and stuff like that. Would I say it's the same as figure 3? It's tough. I think in figure 3 they're extended even more. So I think there'd be it's even a bigger moment of inertia for figure 3 than it is for figure 1. But so there's my thought process. I have batted this one around for a while, so I cannot. I've second guessed myself so many times on this question that it's not funny. I'm confident on that answer. That because omega is squared in the energy equation, a bigger omega squared gives you a bigger effect on there. I tried to do this for a long time, looking at the entire system and looking at the skater as an entire system and stuff like that. But because omega is changing, I think we're confident on that one, or at least I am. But we'll find out tomorrow night. With that, all right. Any questions on this, or are we good to jump back to the other one and then we will go from there? Okay, then I'm very quickly going to try to get back to, where did I paste that question? Did I paste that question? We're all the way down. Keep going. Oh, bottom. Nope. I didn't paste in there. Okay, wow, I screwed up that pretty badly. New page. Okay. Did I save the picture I took? I did. Okay. Copy. The heck is going on here? Paste that picture in. All right, so last one. I'm going to do this kind of in a blur because it is overtime and I don't want to hold you guys too late. But this is the next chunk here. We're talking about our systems. We pull it down from, so L1 is our natural length of the spring. L2 is our equilibrium point where the force downwards and force upwards are equal to each other. And L3, we pull it down to some amplitude from there and we let it go. Consider the time during which the block is moving upwards towards the equilibrium position and the spring length is still longer than L2. Is the total mechanical energy increasing, decreasing, or constant? And explain why. All right. So let's go through this part right here first here. If we just look at the block. The block system, the only thing acting on there that we can include is, well, the force from a spring. Actually, I can't even include the spring, right? We're not, no, there's no spring at all there. So the block system, just the block, has a net force so to increase. You can also say that there is no PEG or PES. So that sort of thing in there. So that one's kind of straightforward. It goes, it has a force, it'll accelerate. I could probably say, well, I should say it does work on it, which does work. There's that right there. So which figure are we observing here? We're looking at it between figure 3 and figure 2, where we have pulled it all the way down and we're going to let it go. And we want to talk about what happens to the total energy. Is it increasing, decreasing, or staying constant for each of these systems, and explain why. Okay, so that's part A. Let's look at part B with this. All right, part B, we are now looking at the spring, and we are looking at the spring and the block. Yes, that's the word, the spring and the block in there. Where is my thing? Anyway, so for part B, wow, I definitely got cut off the page there. I'm sorry. For part B, we're going to say that let's see. So spring-back system has increasing kinetic energy and decreasing potential energy in a spring. Can't talk about PES in part B or PEG because we don't have the Earth included. So we can't talk about any sort of crazy potential energy due to gravity sort of thing going on there. This is tough. Like what we need to say here is that it can't be fully converted because the total energy has to be equal to potential plus kinetic plus gravitational. I don't have gravitational to talk about here. Oh, you know what we can do? There we go. Got it. So we can definitely talk about losing elastic potential energy. We have the spring, so we can talk PES. Yeah. There you go. That's clearer. All right, so because we can't include the Earth in our system, we can't talk about potential energy, but we do have gravity. We do have a force that is acting on it. So because of that, we're having work being done as we rise up that is negative work because it's going in the opposite direction. I'll do MG. Something like that. Okay. Yeah, so we can definitely talk about losing potential energy in the spring. We're gaining some kinetic energy, but we're also losing some due to work. That's part B. So we are losing energy as it rises because of the system we defined. So we're gaining in part A because that block is going faster. We're losing in part B because as the block rises, we are converting kinetic or elastic potential into kinetic, but we're losing some because gravity is doing work on that block too. You definitely could. Yeah, if you want to draw force diagrams out, it would just be tough to, you just got to be careful about which ones you're doing on here. So if I wanted to draw some force diagrams, because why not? We would do something like, if this was case 1, I might do the block and have force on a spring, gravity going down, Fs is greater than mg. For case 2, I would have the spring and the block. The only force I would draw here is gravity, because force on a spring would be an internal force and it would not actually do anything on there. So that's the sort of stuff that we got to be careful about. Is for the block itself, 2 external forces, part 2, 1 external force on there. Jeff, are you talking about case B or case C? Case C, we definitely can. Yes. Something like that. Yeah, you can go further on in that. Yeah, I got distracted. So definitely talking about that sort of thing, rising up and going from there. All right. There was more to this question, wasn't there? So why does A increase again? So because A, we're only looking at the block, there is nothing that we can do to say, to talk about potential energy of any kind. A being the block, all we have to look at the block is kinetic energy. We can't do PES because the spring is not part of our system. We can't do PEG because the Earth isn't included in our system. So all we can do is say, okay, kinetic energy, 1/2 mv squared, and that block is moving upwards and accelerating. It's getting closer and closer to that equilibrium position. So its speed gets increasing faster and faster and faster and faster, which means its kinetic energy goes higher and higher and higher and higher. And therefore, the total energy of that block, which is only kinetic, goes up. We can't say anything else because we can't include any of those other kinds of energy because they're not in our system. Jonas, so in B, is gravity doing positive work as the block goes down? Sure it is. The only trick here, though, is in this part, they told us we are considering the time while the block is moving up, and that's it. Yes, eventually, when we get to that high point and it comes back down, we will have positive work from gravity. We're just not concerned about it in this part. Okay. Then, yeah. All right. I think I'm going to call it for tonight here, guys. I will definitely take a look at that question. Again, Jeff, we'll pull it up and I'll do it a little bit more at our mega stream next week, just to make sure we get over part D and part E. It's going to take probably another 15 minutes to explain it right, and we're already 15 over. So next time is the night before the exam. Yes, 7 o'clock. No, sorry. You guys can start at 4 o'clock. I'll show up around 7, night before the exam. And also there's a 1 p.m. stream day before the exam, open Q&A. You guys are welcome to show up for that one too. So, yep, we got 2 more streams before the exam, and we'll go from there. All right. If you guys have questions, concerns, anything like that, please shoot me an email. My email address is peter@fireball.me. And also check out the community posts. We've had some great interaction so far on there. Try it out. See how you guys are doing with those questions. I actually post this one on there too, just to let us kind of asynchronously go through this too. So I will post that one as well, and we'll go from there. All right. Have a great night, and I hope to see you guys in a week. So see you guys later.